In this video, we will be looking at two things. Firstly, we will look at the moment generating function of the Poisson distribution, and then secondly, we will discuss in the second part of the video, we will discuss the Poisson process. Okay, so by the end of this video, you should be able to derive the moment generating function of the Poisson distribution. You should be able to recognize if we have a Poisson process or if a scenario follows a Poisson process. And then you should be able to calculate the expected number of events during a fixed time interval. And you should be able to list the assumptions of a Poisson process. Right, so the key concepts, it's time interval, number of successes in a time interval, approximate distribution, Poisson probability distribution, Poisson process, and Maclaurin infinite series expansion of that exponential function there. Right, so we will start with the moment generating function, as these are the 4 bullet points that you need to know or be able to do by the end of the lesson. So proposition says the moment generating function of a random variable x that follows a Poisson distribution with parameters lambda is given by that formula there, where the moment generating function is equal to e to the power lambda times e to the power t minus 1. So this is the moment generating function of the Poisson distribution. Again, every distribution has its own moment generating function. And it's important that you know how the moment generating function of each distribution looks like. Right, so let us prove this. So by definition, the moment generating function is defined as the expected value of e to the power tx. Now this is equal to, by definition of the expected value, it's equal to the sum of the product e to the power tx times the function of your PMF for all possible values of x. Alright, now this is equal to the sum again, where x goes from 0 to infinity, of e to the power tx times e to the power minus lambda times lambda to the power x divided by x factorial. Right, so we said that if we have a constant, what do we do then? We will take that constant and then put it right in front of the summation sign. And so we have here e to the power minus lambda times the sum of x goes to 0 to infinity of e to the power tx times lambda x, all divided by x factorial. Alright, so we see that we have 2 items here, all to the power x, or the power here it's x, and so we can group these 2 items, right? Okay, so we have here e to the power minus lambda times the sum, where x goes from 0 to infinity, of lambda times e to the power t, all to the power x, right? So lambda x times e to the power tx is the same as lambda et all to the power x. So that power there can go to those 2 items, the lambda and e to the power t. So that is what we have there. Alright, so we have learned a couple results. One of them is that the summation of I going from 0 to infinity of ui divided by I factorial, that is equal to e to the power u, regardless of what that u is. Alright, can we use this expression here? Can we use it to simplify this derivation? Okay, so let us look at some of the similarities. So we have the sum of x equal to 0 to infinity. Okay, x equal to 0, I equal to 0, yes. And then both the summation goes to infinity, yes. And then we have in the numerator lambda e to the power t to the power x, and we have x factorial. Okay, so the denominator must be x factorial, good, since there we have I factorial where I goes from 0 to infinity. Numerator mu u to the power I, and the numerator we have that item there to the power x. And so we could say, using this result here, that that sum is equal to lambda e to the power t. Isn't that true? U, in this case, it's lambda e to the power t. And so we will say that this is equal to e to the power minus lambda times e to the power lambda et, since the sum of I equal to 0 to infinity of u to the power I divided by I factorial is equal to e to the power u. In our case, we had the sum of x going from 0 to infinity of lambda times e to the power t all to the power x divided by x factorial, that is equal to e to the power lambda times et. Alright, so now we have then the moment generating function of a Poisson random variable is given as e to the power lambda times e to the power t minus 1. So you can simplify that product there, and at the end, yes, we have proved that the moment generating function of a Poisson is given by that. So, for example, let's say the moment generating function of a random variable x is given as e to the power 2 e t minus 1. And then from this moment generating function, if you're just given the moment generating function, we could ask you to calculate the probability that x is equal to 2. We can ask you to calculate the expected value as well as the variance. We can even ask you to calculate probability of x it's greater than 6 or any other probability. If you're just given the moment generating function, how are you going to do it? You will use the uniqueness property that says every distribution has its own unique moment generating function. So we know that now, since we have derived it, the moment generating function of a Poisson, it's in that format there where we have e to the power lambda to the power lambda times e to the power t minus 1. So if you see a moment generating function of this form here, you should immediately spot that this is the moment generating function of the Poisson distribution. Alright, so exercise 108 says use derivatives of the moment generating function to obtain the mean and variance of the Poisson distribution. Alright, so let's start with A. The moment generating function of the Poisson, we derived it as e to the power lambda times e to the power t minus 1. Alright, so the power of e, it's lambda times e to the power t minus 1. And so if we then get the first derivative, right, so this is the derivative of the moment generating function with respect to t. That is the derivative of that function there, e to the power lambda times et minus 1. And so, in a way, you're deriving this expression, e to the power lambda et times e to the power minus lambda. Right? Okay, so now the derivative with respect to t, since e to the power t is in the power there, then the derivative in this case of the exponential function, it will be equal to lambda of e to the power t times then the function. Alright, so that's the first derivative of the moment generating function. Then the next step is to substitute t equal to 0. And so we have lambda times e to the power 0 times e to the power lambda e to the power 0 minus 1. And so that is equal to lambda times 1 times e to the power lambda 1 minus 1. So at the end we have lambda times e to the power 0, and so the expected value is equal to the first derivative of the moment generating function when t is equal to 0, and that is equal to lambda. So we just proved that the expected value is equal to lambda using the moment generating function. Right, so now the variance, for us to get the variance we know by definition is equal to the expected value of x squared minus the expected value of x all squared. So the expected value of x squared is the second derivative of the moment generating function when t is equal to 0. So we will deriving again this the first derived function. So we're deriving for the second time. So we're deriving lambda times e to the power t times e to the power lambda e to the power t minus 1. And so the first derivative we have the derivative of this expression here, item, times that function plus the derivative of the second function times the first function. Okay, so what I'm saying is the derivative of fw times hw then equal to the derivative of f firstly times h plus the derivative of h times f. Okay, so if this is our f, supposedly our fw, and this is supposedly like our hw, in this case ht or ft, then the first derivative then of our first function there, it's lambda, the derivative of e to the power t, we're deriving, remember, with respect to t, so the derivative of that of e to the power t is 1 times e to the power t, right? Okay, now we're deriving, we're multiplying by the second function to the power t minus 1 plus the derivative of the second function, which is lambda e to the power t times e to the power lambda e t minus 1. Then we will multiply it by the first function, which is e lambda times e to the power t. Okay, so again, we have, if we have two functions, then the derivative with respect to that variable there will be the derivative of the first function times the second function plus the derivative of the second function times the first function. Okay. So we have essentially done that. T prime t plus prime t times ht. And so then this is equal to lambda of e to the power t times e to the power lambda t minus 1 plus lambda, lambda times e to the power t squared times e to the power lambda minus 1, right? Okay, so this is then our second derivative. So this is our second derivative with respect to, derived with respect to t. And so now if we substitute t equal to 0 here, we have lambda times e to the power 0 times e to the power lambda, e to the power 0 minus 1, plus lambda times e to the power 0 squared times e to the power lambda, e to the power 0 minus 1. And so at the end, what we have lambda times 1 times e to the power lambda 1 minus 1 plus lambda squared times e to the power lambda 1 minus 1. So at the end, you have lambda plus lambda squared. Isn't it true? So you have lambda plus lambda squared. And so the expected value of x squared is equal to lambda plus lambda squared. Now the variance is equal to expected value of x squared minus expected value of x all squared. Now this is equal to lambda plus lambda squared minus lambda squared, which is lambda plus lambda squared minus lambda squared, and that is equal to lambda. Okay, so we have just proved then that the variance is also equal to lambda. So the expected value is equal to the variance, and they're equal to lambda if x follows a Poisson distribution with parameter lambda. Happiness? Alright, so if I lost you somewhere, especially with the derivatives, because it does seem like it's a lot when you have two functions. If you are confused anywhere, do let me know or post on the discussion board. Now, in the second part of the video, we will look at the concept called a Poisson process. Here we are interested in calculating, firstly, counting the number of events or successes that during a particular period of time or space. And we're interested in calculating the probability of observing those number of successes at different periods of time or space. All right. So a proposition says, suppose that you have then a PMF of this expression there. So we have the PMF equal to e to the power minus alpha t times alpha t to the power k divided by k factorial. So we have here a function equal to e to the power minus alpha t times alpha t to the power k all divided by k factorial. Okay, which is similar to our PMF of the Poisson, which is e to the power minus lambda times lambda to the power x divided by x factorial. Okay, so that's pk, here it's px. Alright, so it says here that suppose that you have that function there, so that the number of pulses or events or successes during a time interval of length t is a Poisson random variable with parameter lambda equal to alpha t. So our lambda is equal to alpha t. Okay? Then the expected number of events during any such time interval is then alpha t. So t, that t, it's length, or it represents time, or some interval or length of time, right? So the expected number during a unit interval of time t is alpha. So for one or unit interval of time, the expected number of pulses or events or successes is alpha, and the expected number of successes or pulses or events at any time will be given as alpha t. Alright, so with the Poisson process, it says here that the number of events occurring during a fixed time interval of length t has a Poisson distribution with parameter alpha t. So the number of events, or the number of successes that occur during some fixed time interval of length t. So time is involved, time or specific space is involved. Then we will say that that random variable has a follows a Poisson distribution with parameter alpha t. So essentially what we're doing here is changing the value of the parameter lambda for specific periods of time. So if lambda is 2 in 30 minutes, then what would lambda be for 1 hour 30 minutes? So that is what we want to calculate or observe. So the Poisson process says any process that has this type of distribution is called a Poisson process, where alpha is called the rate of the process. Right, so the rate of the process, or the number of successes or events that happen in a unit interval of time, that is given as alpha. Right, so let us have a look at a couple of examples so that this is clear to you. Okay, so suppose the number of power outages in Tshwane on average is 4 per month. So if we tell you that on average we have 4 outages per month, essentially we're telling you that the expected value of x, if we define random variable x as the number of outages for the specific period or per month, then the expected value of x, which is lambda, that is equal to 4, right? So here we have then essentially the firstly tell us that the expected value of x, which is also equal to lambda, that is equal to 4, since they said on average we have 4 per month. All right, now give the rate of the process as well as the expected number of outages in 3 months of the year. So the rate of the process, it's defined as alpha, and alpha, it's the number of events that occur in this one unit. So in 1 month we're expecting 4 outages, so alpha is equal to 4. Now the Poisson process comes in when we change the time. So now we're no longer working with per month, we are interested in the number of events that would occur in 3 months, right? So the Poisson process says then lambda will be equal to alpha times t. In this case, t is equal to 3 months. So how many, or what is then the expected number of outages in 3 months? In this case, I'll call it x star, that is equal to alpha t, that is equal to 4 times 3, which is 12 outages in 3 months. Okay, then the next example, suppose that on average, we have 6 births per day. All right. Now give the rate of the process. So we will start with 6 per day. And now with the Poisson process, it says that lambda then will be equal to alpha times t. So we want to know what is expected number of births during any given week. Then what is lambda for any given week? Is equal to alpha times t. In this case, we have 6 times, so in a week, okay, so we have here the rate of the process is equal to 6 births per day. And so the Poisson process says for any given week, lambda is equal to alpha t. So lambda for any given week is equal to 6 times, what is the time now for a week? If we have 6 per day, then in a week you have 7 days, right? 6 times 7. And so our lambda changed from a rate of 6 to then another rate where we are looking specifically at the number of births per week. And so we will say that we're expecting on average 42 births per week. All right, do you understand what we're doing now? So the Poisson process, we are calculating then the expected number or lambda for a specific time period. Okay. Sorry. Now the next example is on the meteorites, where it says that approximately 0.56 meteorites strike Earth every hour. So every 1 hour we have 0.56 meteorites every 1 hour. Give now the rate of the process. How would the process change? So if we have 0.56 every hour, then for 2 hours you have 0.56 times 2. So the process will change at a rate of 0.56. Do you see? All right, so now what is then the expected number of meteorites that would fall in a randomly selected 24-hour period? So if we have 0.56 per hour for 1 hour, in 24 hours, how many would you have? Okay, so our lambda now would change from 0.56 to alpha times t. That is equal to 0.56 times the time period here is 24 hours. And so we'll be expecting on average 13.44 meteorites per day or 24 hours. Then the last example, suppose that trees in a forest are more or less evenly distributed with an average of 291 trees per hectare. Give the rate of the process. Okay, so in this case, we're starting off with an average. They tell us on average, which is lambda, expected value of x, which is equal to lambda. We have 291 trees per hectare. All right. Now the Poisson process then says that lambda will change at a rate of alpha equal to 291 trees per hectare. And so for a given space, in this case, we want to know what is the expected number of trees in a randomly chosen acre. So we have that 1 hectare is equal to 2.4715 acres, meaning we have about two and a half acres that will make up 1 hectare. Then you have those trees in there. All right, so we have 2.5 acres. This makes up 1 hectare. Okay, so now how many trees? What's the expected number of trees in 1 acre? If for 1 hectare you have 291, then in one acre, how many? Per acre, how many would you have? Okay, so we have here 291 trees in 1 hectare. We see that the rate alpha is equal to 291. Now, this is the same as 291 trees in 2.47105 acres. It's exactly the same. So 1 hectare is equivalent to 2.47 acres. Now we want to know for 1 acre, how many trees will we have here? So you can divide by 2.47105 divided by 2.47105, and so you're expecting on average 117.8 trees, or about 118, but do leave it as, with decimals. Okay, so in this case our lambda now went, in this case when we're looking at acres, it went from 291 to 117, and that is equal to alpha times t. Alright, so do you understand the Poisson process? So with the Poisson process, essentially what we're just doing is we are recalculating the value of lambda for specific time periods. Okay, that's why we have that alpha t, and lambda is equal to alpha t. So you should be able to calculate lambda for different periods of time or space. All right.